All right, today is Wednesday, August the 28th, and this is your unit test review for measurement and data. What I would suggest with the review is that you, if you come to a screen where you did not do this in class or practice it in class or feel like you need more practice, then you go ahead and do this screen, then pause it, and then unpause so that you can check your answers. The top portion is dealing with significant figures, and I'll just real quickly kind of restate some of the rules and the ways that we remember this. First of all, 0.092. Beginning zeros do not count as significant, so for this one, you only have two significant figures here. All right, and so you would express that as 2. Those beginning zeros do not count. The second one down, 80,900, that 0 that is in between the 8 and the 9 is sandwiched, so it does count as significant. However, ending zeros in a whole number do not count. So this one would have 3. 5,700, ending zeros do not count in a whole number, so this one would only have 2 significant figures. Now, looking at the Atlantic Pacific rule, if that's something that you use, 0.00350, you have a decimal place present here. So you're going to go to the Pacific side and work your way in. When you get to your first non-zero digit, which is the 3, you count that and everything after. So this one has 3 significant figures. Same thing for this one. If the decimal place is present, you go to the Pacific side of the number, work your way in. Here, your 1 is your first non-zero, so that, and everything after that counts as significant. So that one has 5. 101.00, because you have that decimal, those ending zeros count as significant, so there are 5 here. Beginning zeros do not count as significant in a decimal, but ending zeros do, so there are 4 here. And beginning zeros do not count, so there's only 1 there. All right, performing the calculations. Let's pull up the calculator. And I wanted to go ahead and put this in so you can see it on the calculator and go ahead and get the answer there. So you have 1.0 times 0.850. Hit enter, and you get 0.85. You're going to divide it by, make sure you put that bottom portion in parentheses, 0.08206 times 298. Make sure it's all in parentheses. That ensures that your calculator is treating it as one number as that denominator. Hit enter, and you get a number that looks like 0.0347593,102. Now, when you are looking at what you need to express, you have to look at the significant figures that are in your number. So here you've got 2 significant figures. Here you've got 3 significant figures. In this value on the bottom, you've got 4. And in this value, you have 3. So you would need to round that answer to 2 significant figures, because right here is your least precise measurement. Now, in order to do that, your 2 significant figures are going to be the 3 and the 4. So you would keep that as 0.034, and then the 7 would round the 4 up to a 5. So this is expressed as 0.035. And that would be your answer. Okay, for the next, when you put this into your calculator, you're going to get a number that looks like this. Let's go ahead and put it in. you've got 2,600 divided by, make sure that bottom portion goes in parentheses so the calculator treats it as it should. So 24.27402 008. Now, as far as significant figures go, this top one has 2 significant figures. This one has 4, and this one has 3. Because you're multiplying, dividing, you're looking at how many total significant figures. Here is your least precise measurement, and you have to round your answer to 2. So you keep the 2 and the 4, and you basically are dropping the rest of this. So this is going to be expressed as 24. Bottom one, when you are adding, you are looking at places past the decimal. So 94.7 plus 8.3 is equal to 103. And this is how it looks in the calculator. So 97, oops, 4.7 plus 8.3. So obviously you have to put in there correctly. Hold on. Plus 8.3. All right. When your calculator shows you that, it's showing you 103, which is not as precise as your measurements, because your measurements here are showing you that you have one place past the decimal here and one place past the decimal. So because you're doing plus minus, you're looking at places past the decimal. So for this one, you would have to change this to 103.0. So that's an instance in which you would make this your answer more precise than the calculator was showing you. Okay, for this one, and I had taken these off, the bottom ones, didn't really want you guys to do these. So that bottom section is off of this. Now, write the following numbers in standard decimal notation. If your exponent here is a negative, that means that this decimal is going back 1, 2, 3, 4. And that means you fill in with zeros. So that number is expressed as 0.1234, and then you write your 29. Your exponent being positive means that the decimal place that is here is going to move to the right 1, 2, 3 times, and that fills in with zeros. So that is written as 9,000. This one just stays as is because that exponent of 0 tells you the decimal place does not move. This 8 tells you that that decimal moves to the right 8 places. So 1, 2, 3, 4, 5, 6, 7, 8. And this -1 tells you that decimal moves to the left 1, so that's 0.21665. And the 2 being positive means that decimal place moves to the right 2 places, so that should be written as 500.5. Now, putting into scientific notation, you always want to have one place only in front of the decimal point. And then you're going to tell with your exponent what you would do with that decimal to get it back to its original location. Since this has already got one place or one number in front of the decimal, you're just going to write it times 10 to the 0 because you wouldn't change that. And this one, if you put your decimal place here, that would be 2. Okay, do not put 2.0 because remember that those zeros on 2000 are not significant. So 2 times 10, and you would move that decimal 1, 2, 3 places to the right to get it back to its original location, so to the +3. This would be 1.5 times 10 to the first. Okay, this one would be And you want to write anything that is significant. Since all four of those are significant, it's 6.589. That decimal place would go 1, 2, 3, 4, 5, 6 places to the right. So times 10 to the 6th. All right, this one, your 9. And since there is nothing that follows that 9, oops. Okay, sorry, I had the pen writing all over the place. This one right here, since your 9 here is the only one in that number that is significant, that is all that can show at the beginning. So times 10, and if you move your decimal place here, it's going to have to go to the left 1, 2, 3, 4 places. So to the -4. And then these two are significant here, so that's written as 9.2 times 10 to the, and that would have to go back 2 places, -2. Notice that anytime your number is written in scientific notation, there is no number other than, there's just one number in front of the decimal, and that's why I took the ones down here off, because I'm not sure why those are written that way. Scientific notation should only show one number in place in front of the decimal, and then any other numbers that were significant in that measurement. Okay, when you are reading measurements, you have to read all of your known digits plus one estimated. So your known digits are the ones that are marked on the device. So for this one, your 3 is marked here, and so that you know it is 3 point, but you're estimating where that line falls. So I would estimate 3.7 centimeters. Remember that this last one, that 0.7, this is an estimate. So somebody else's could say 3.8 and so forth, but you only can have 2 significant figures in that measurement. You don't need any more. The one to the right of that, you have got the 4 that's marked, and then you have 2 lines over that are marked, so 4.2, and this appears to fall right on the 0.2, so my estimate would be a 0. That last one is estimated. Somebody else could say 4.21. Somebody else could even say 4.19. But that is estimated, that final one. So you would definitely have 3 significant figures in that measurement because of that tool. This one is showing 20, so your 2 is a known. Then you've got 1, 2, 3, 4, 5 places that pass it. So 25. And I would say that that line falls a little bit beyond the 25, so 25.2. Somebody else could say 25.1. Remember that last number is an estimate, but all of those are significant figures. And then this final one would be 0. And your 5 is a definite. So it's falling somewhere between the 0.5 and the 0.6. So 0.5, maybe 1. Because this 1 is an estimate. You know it went past that 0.5. So for this ruler, you've got 2 significant figures that need to be expressed. This one will show 3, this one will show 3, and this one will show 2. So again, when you're reading any type of tool, all known digits plus 1 estimated. When you go down to your graduated cylinder, remember that you want to read the bottom of that curve. Know what your line means. So between 100 and 200, that means that this other bold line is representing 150. So we go up, we know this is 110, 120, 130, 140. So we know the 1 and the 4 are definite, and we know it falls a little bit under the 150, so we could say it is 149. That 9 is an estimate. You cannot record any more digits there. Okay, we know that this is 40, and these go up by tens, by ones, so 41, 42. So we know for sure that the 4 and the 2 are there. And then we can say 0.1 because it looks like it's a little bit above. Somebody else might come in and say that looks like 42.0. But the fact of the matter is this has 3 significant figures, and so does this one. The last one is always estimated. For this one here, understand that your scale is showing between 1 and 2. So like this long would be 1.5, and then this longer bold line would be 0.5. So what you're going to be showing is 0 point, and it goes up. You know you're at 5. This is 5. This is 6, and this is 7. So 0.7, and then it falls a little bit in between the 0.7 and the 0.8. So you go by a tenth, 0.7, and I would say maybe 4, because it doesn't look like it's necessarily exactly half. But again, somebody else might say 0.75. So that reading would have 2 significant figures. The thermometer on the end goes up by ones. So you've got 1, 2, 3, 4, 5, 6, 7, 8. So you know you have 8 degrees Celsius. It's between 8 and 9. It falls a little bit below half for what I think, so I would say 8.4. Again, remember that is your estimated number. All the known numbers should be the same for everybody. The estimated number might be a little bit off, but regardless, you have 2 significant figures there. Okay, for this slide, you're dealing with accuracy and precision. So the data is going to be reported as an average. So you need to get the average for groups 1 through 7. So you're going to go group 1 was 12.53. Group 2 was 12.82. Group 3 was 11.78. 11.95. For group 4, group 5 was 12.02. 6, 12.10. And 7, 11.83. Okay, that gives you the total there. You want to remember this is an average, so there are 7 groups. We're going to divide by 7. Okay, and you get a number that looks like this. Now, since all of those had 4 significant figures, then your average should show 4 significant figures, and you want to round to 12.15 because that 7 is going to round up to a 5. And that is going to be your average that is expressed there. Make sure I got the right number. No. All right, that's the average that is expressed there. Now, the plus minus is telling you your deviation. How much did you deviate from, or how much did each group deviate from that average? And the first thing that you have to do is get a standard deviation for every group. So for group 1, the deviation is going to be, and I'm just going to mark this as deviation. So I'm going to get each group's deviation. So 12.53 minus 12.15. So in order to get the deviation, you're going to subtract that from the average. And this group deviated from the average by 0.38. You're doing the same thing here. This group deviated by 0.67. This group deviated by 0.37. This group by 0.20. This group deviated by 0.13. This one by 0.05. And this one deviated by 0.32. Now, one of the things that you want to look at is the fact that we're not subtracting like numbers on a number line. We're finding the difference between two measurements. So you're not going to record any negatives. In order to get your standard deviation, which is your plus or minus, you're going to take all of those. So 0.38 plus 0.67 plus 0.37 plus 0.20 plus 0.13 plus 0.05 plus 0.32. So you would get 2.12. There are 7 sets of data, so divide by 7. And the standard deviation for this is 0.30. So that's what would go here. And what that is telling you essentially is that 12.15 is the average for that group. And each of the individual measurements deviated from that average by about 0.30. Okay. Now, if the accepted, and we're going to be using group, this one says group 1, so we're just using group 1 here. It says if the accepted mass is 12.15 grams, what is the percent error of group 1's measurement? So what you have to do is you take the average that you found for group 1, or you take group 1's actual measurement, so it was 12.53 grams. Then you are going to subtract out what the accepted mass is. So the accepted mass here is 12.15. Divide by the accepted mass, 12.15, times 100, because this is a percent. So you're going to take the top part, okay, that 0.38 is your error. That's how far away you got from what the intended target would be. That's how far, if it was a bullseye, that's how far you got away from the middle. Now to get a percent, you're going to divide it again by the actual number and multiply that by 100. And that gives you an error that is 3.1275. If we recorded it with the correct amount of significant figures, since all of those masses have 4 significant figures, we would record this as 3.128. So that is the percent error there, 3.128. Okay, remember that your percent error is telling you how accurate your group's measurement was. Okay, So Mr. Rutherford's class obtains an answer of 12.05 plus or minus 0.45 grams. The result of Mr. Rutherford's class has what type of precision in comparison to Mr. Dalton's class? So if you're comparing the two, you look at Mr. Dalton's class, and that one has 12.15 as an average and a variance or standard deviation of 0.30, and their percent or their accuracy is measured as this, whereas Mr. Rutherford's class, and it's not it has nothing about accuracy, it's asking about precision. So this is the only thing that you're looking at for precision. So even though theirs was a little further away there, their precision was not as good. Yeah. So 0.45 in comparison to 0.30, that's what you're using for precision. So they had less precision than Mr. Dalton's class. Okay, for your metric units, length, and I'm just going to write the base unit. The length is meter, centimeter, millimeter. Mass is gram. You can use milligrams or kilograms. Volume is the liter, the milliliter, or centimeters cubed or meters cubed for the volume of a solid. Time is seconds, minutes, hours. Temperature is in Celsius, degrees Celsius, or Kelvin. Can be also a temperature unit. Now, completing the conversion factors. I'm going to do it with, some of you would probably do this moving the decimal place. I'm going to do it with dimensional analysis. So I start off with 1 decimeter here. And I know that in 1 meter there's 10 decimeters. So I have to put that so my decimeters will cancel out. 10 decimeters in 1 meter. That cancels out. So basically 1 divided by 10 means I take my decimal place back 1. So that's 0.1 meter. 1 kilogram, and this is just straight up. This is something that you have to know. So in 1 kilogram, there are 1,000 grams because the prefix kilo means exactly 1,000. All right, if we want to take 1 milliliter, we have to know that there's 1,000 milliliters in 1 liter. So essentially to get from milliliters to liters, we divide by 1,000. So take our decimal place back 3. So 0.001 liters. And for 1 centimeter, again, we have to know that there are 100 centimeters in 1 meter. That cancels out. So 1 divided by 100, take your decimal place back 2. So that's 0.01 meters. Okay, as far as metric conversions go, you have to know your conversion factors. You have to know that in, oh, it's doing it again. Okay, so once again, you have to know that in 1 kilogram is equal to 1,000 grams. So using that, you know, your given is always written down first, whatever's given. So we know our measurement's 2.50 kilograms. We've got to get it to grams. This conversion factor needs to flip so that kilograms. All right, so you're putting that conversion factor so your kilograms will cancel out. 1 kilogram on the bottom, 1,000 on the top. So that cancels out kilograms. Multiplied by 1,000 means your decimal place moves 3 places to the right. So that's going to be 2,500 grams. In 1 kilometer, same thing. There's 1,000 meters. So you set this up the same way. Always start off with what you know. You know the measurement is 12.6 meters. Put your conversion factor, so meters is on the bottom. And therefore you can cancel it. This means you're going to divide by 1,000, move your decimal place back 2, so 0.0126. Okay, the bottom one, 1 milliliter is equal to 1 centimeters cubed. So therefore this is, the answer is simply 70.6 centimeters cubed. Up here, 1 liter is equal to 10 deciliters. So you're starting with a known measurement of 0.350 deciliters, and you've got to get that to liters. So you've got 10 deciliters in 1 liter. That means that you're dividing by 10, your decimal place is going to go back 1. Okay. And then for the final one, you've actually got 2 conversion factors that you are going to use to best do this. So in 1 meter, you've got 100 centimeters. And in 1 kilometer, there's 1,000 meters. So sometimes you've got to use multiple conversion factors. So start off with what you know. You have 2,570 centimeters. There's 100 centimeters in a meter. And there's 1,000 meters in a kilometer. Centimeters cancel out. Meters cancel out. So you're dividing by 100, which means your decimal place goes back 2. Divide by 1,000, goes back 3 more. So this is 0.02570 kilometers. And the last thing you want to look at is if you go from a larger to a smaller unit, your number should get larger. If you go from a smaller to a larger unit, your number should get smaller. Okay, this one is using dimensional analysis to solve conversions. And for this one, you've got 1.8 weeks. And you always want to start with okay, let's see if this does any better. The pen situation is not working well. All right, so you always write down with what you write down what you're starting with in the units. So I would say we need to go from weeks to days, days to hours, hours to minutes. So we know that we have so weeks to days, we have 7 days in a week. 1 week goes on the bottom, 7 days on the top. If I calculated that, that's going to give me how many days. So from days to minutes in 1 day, or days to hours first, we have 24 hours. That'll give me hours. And in 1 hour, we've got 60 minutes. And so in the end, it is what I wanted at. And so when I calculate this, I'm going to take it and I can do exactly the way this shows. I can put it in parentheses, your conversion factor, or since all of these conversions have the number other than 1 on the top, I'm just multiplying. So 1.8 times 7, that answer times 24, and that answer times 60. So I got 18,144. And my unit is minutes. Okay, now since when we're dealing with dimensional analysis, the only thing that you can use as far as significant figures is going to be your beginning. So since we only had 2 significant figures in our initial measurement, we can only have 2 in the final. So if we had to express this using the correct number of significant figures, it would be 1,800 minutes. Okay, I marked this off for this one because I didn't want to get too confusing. So we're starting off with 135 centimeters. using this conversion factor. I'm going to put the centimeter one on the bottom. There's 2.54 centimeters in 1 inch. So that cancels out. And I've got 135. And I can just multiply by the conversion factor. For those of you who it just confuses you as far as how to set this up, just put it in the calculator exactly the way you see it. 1 divided by 2.54, parentheses, and that comes out to 53.14960. Now, again, you started off with 3 significant figures, so you should round your answer to 3, which would be 53.1. inches. All right. Now, the bottom one is just kind of showing you how you can go through random units, even if you are not really familiar with them, because eventually you will get to some conversion factors you're not familiar with. So always start with what you have, which is 825 inches cubed. And then you're going to go from there to it wants to know firkins. So the first one I'm going to use is this one, that there's 231 inches cubed in a gallon. Okay, when I calculate that, that gets me away from inches cubed and gives me gallons. Now, to get to firkins, I want to go from gallons to barrels. And you're setting it up so these can cancel out. And in the end, in 1 barrel, there's 4 firkins. And once that cancels out, you just pull up your calculator. You've got 825, and then you can put it in exactly as you see it, in parentheses 1 divided by 231 times, in parentheses 1 divided by 42 times, and you could just do times 4, or just to follow the consistency, put in parentheses times 4 divided by 1. That way everything goes in the calculator as you see it. So this comes out to 0.3401. You always want to go by your beginning, which your beginning is telling you that you have 825 significant figures. So your calculator said 0.34013. So that is going to round to 0.340. And your unit is firkins. Okay, so here you're looking at a graph and you're looking at density of ethanol versus water. So when you are looking at this, water always has a density of 1 gram per milliliter. And here, your ethanol has a density of and it always has a density of 0.789 grams per milliliter. Because if you take this number, which is your mass, take your mass across, which is a little bit less than 40, divided by 50, you're going to come out to 0.789. And at any point with your water, it's 10 divided by 10 here, 20 divided by 20 would be 1, and so forth. So which one would form the top layer? Your ethanol is going to form the top layer because it's less dense, and then water is going to sink to the bottom. So the smaller the density, the more likely that it is to float. The density of ethanol is less than the density of water because it's at 0.789. If you had a 50 milliliter sample of each, the mass of ethanol is going to be less than that of water. So let's say that we did a calculation and mass is equal to density times volume. So if we go with ethanol first, and it's saying that we have a volume of 50 milliliters, and we know that ethanol has a density of 0.789. The mass of ethanol is equal to the density, which is 0.789, times the volume, which it says you have a 50 milliliter sample. So the mass for that is going to come out to be 39.45 grams, and that's for ethanol. If we do water, our mass is equal to our density, which is 1.0 times our 50 milliliters, and that comes out to be 50.0 grams. Okay, so the mass of ethanol is going to be less than the mass of the water. If you have a 50-gram piece of tree bark that floats on water while a 50-gram piece of bone sinks, list the water, tree bark, and bone from least to the most dense. So your least dense is going to be the tree bark. Your water is in the middle, and bone is going to be at the end. So the most dense, because it sinks, is the bone. The tree bark floats, so it's the least dense, less dense than water, and water comes in between. All right. The volume of the piece of tree bark it's actually greater than that of a piece of bone. So let's say that you wanted to figure this out. Volume is mass divided by density. And let's say we just put in any given mass. Doesn't matter what it is, it'll come out the same way. So for aluminum, 50 divided by 2.7, which its density is going to give you a volume of 18.5 milliliters. So this one's for aluminum. And for zinc, you're going to take the mass, again, same mass, because we're comparing, divided by the density, and that's going to give you 7.0 milliliters. So the volume of the piece of tree bark, never mind, scratch what I just did. The volume of the piece of tree bark is greater than that of the piece of bone. I was going ahead of myself. We are looking down here. Consider a block of aluminum where the density is 2.7 and the block of zinc is 7.4. If the two blocks have the same mass, which has a greater volume. So that's what I was doing up here. Okay, so aluminum here would have a volume of 18.5. Zinc would have a volume of 7.0. So the one that would have a greater volume is aluminum. If both blocks have a volume of 1.5 liters, which has a greater mass, well, since mass is equal to density times volume, whichever one has the greater density is going to have the greater mass. So that is going to be zinc. Okay, last page. In order to determine this, in order to answer the question at the bottom, you've got to determine the density. It says use the data to identify the metal in the block. So you've got to, I'm sorry, not the bottom question, the top one. We are going to look at the data and determine what the density of this metal block, because it's just saying it's a random metal block here, and we want to see which metal, aluminum, copper, iron, or gold. So we know that the mass is 54.48 grams. We have it's a regular shaped object, so length times width times height. And we're just going to multiply them together, so 3.55 times 1.55 times 1.11. And when you do that math, you have to use significant figures because each of these are measurements. Okay, so you're going to come out to a number that looks like that, 6.107775. and you want this to have the correct amount of significant figures. Each value has 3 significant figures. So you want your answer to have 3 significant figures, so that comes out to 6.11 centimeters cubed. And so your density is mass divided by volume, which is 54.48, divided by 6.11. That's grams centimeters cubed. And that comes out to 8.91653, and it keeps going. You want to round that to 3 significant figures because of those 3, and that's going to round to 8.92 grams per centimeters cubed. And the final one is asking for mass. So when you do your density triangle, remember that looks like this, D, M, V, and you cover up the M. That is going to tell you density times volume. So mass equals density times volume. The density is 4.5 grams per centimeters cubed times the volume, which is 35.0 centimeters cubed. And gives you 157.5. When you take 157.5, each of these values have 3 significant figures, so you have to round that to 158 grams. And that is all of your review.